Hello, good afternoon, everyone.
Good afternoon, sir.
Others are joining. They have come to office, or some of them are on leave. Shall we begin now? Hope they will join in the meantime. Okay.
Maybe they'll join after some.
Yeah, yeah. Okay. Today we shall see a very interesting binary search tree. Uh, these binary trees are called as AVL. This stands for two computer scientists by name Adelson, Velsky and Landis. So these are two Russian computer scientists who devised this AVL trees. Now with normal binary search trees, I mentioned to you, the trees tend to become skewed. That is, they tend to become one-sided. For example, if I add 20 in the beginning and then start adding larger numbers, let's say 30, then 40. As you construct the binary search tree, you have to put larger number onto the right of 20. So when you do this, you will see that this tree is skewed. It is aligned only on the right hand side. Now this uh, resembles the that of a linked list. Okay. Now in such a binary tree, if you try to search, this will take not log n time. This will take time of the order of n. Whereas the regular balanced binary tree would take log n time. Now if you compare these two computing times, suppose you have 100 elements. So O of 100 is 100 comparisons, whereas log of 100 with base 2, it is somewhere between 6 and 7 and 8, or 6 and 7. So at the most you would require only 7 comparisons as compared to the skewed data structure, which results if you don't balance it out properly. So what are AVL trees in the first place? So AVL trees are those trees where the difference between the height of left subtree and the right subtree, if it is confined to plus or minus 1, or in the range minus 1 to plus 1, then such binary trees are called as AVL trees. We shall see what is the meaning of this. Now consider this binary tree here. You have the root at the center, and you will have a lot of nodes here on the left as well as on the right. I have just symbolically shown it as a triangle here. Now if you find the height of the left binary tree, which turns out to be HL, and height of the right binary tree, which is HR, now the difference between the two, HL minus HR, if it is between plus or minus 1, that is 0 is also included, it can be minus 1, plus 1 or 0, then we say this binary tree is height balance and we call it as an AVL tree. Now how do I achieve this balancing of the heights? That is through operation called as rotation. Let's consider this particular binary tree here. Now there are many types of rotations. We shall see first left rotation. When do we require left rotation and when do we require a right rotation? Let us say we have 30, then 20 and 10. Now you will see that this binary tree is skewed onto the left. Okay. Then how do I balance it out and still make it a binary search tree? If you see, if I can rotate this tree like this around the left child, then after rotation you will have 20 on the center, 10 on the left and 30 on the right. So this is the root node now, and this will be the right child and this will be left child. Now if you find the height of left child, which is 1, and height of right child, which is again 1, you will see that the difference is 1 minus 1, which is 0. Whereas if you consider this particular binary tree, the height of this was 1, 2, 3, and here it was 0. Okay, So 3 minus 0, or if you consider this as 0, 1, 2, this is also fine. So 2 minus 0 is 2. Obviously you will see that the difference between height of left subtree and height of right subtree is more than 1. Okay, in that case this is unbalanced. To balance it out, you have to perform the rotation. Now this should have been a right rotation. Okay, so we are rotating the node onto the right. Similarly, the left rotation would be required if you have elements on the right hand side. For example, you had 10, 20, 30. Okay, so this is also binary search tree, but it is unbalanced. Now we have to perform a left rotation around this node. So you will have 20 at the center, 10 again at the left, and 30 on the right. So this is also balanced. So after you insert the elements, you may require some rotations. Now these are simple left right rotation. Sometimes you may require a combination of left rotation and right rotation. So here are some examples which are given here. Now if you observe this, I showed you 30, 20, 10. You required a right rotation. That is, if you turn this, this is what we saw. Okay, but suppose the tree is initially like this, 30 here, 10 here, and 20 here. Now here you require a left rotation first. So you have to left rotate this part of the tree. That is, you bring 20 here, and actually when you rotate this, 20 will come here and 10 will come as a child of 20. Okay, and then perform a right rotation around this 20. Then you will have a balanced tree. So depending on what is the initial shape of the tree, you require only right rotation. Sometimes you require left rotation and then right rotation. On the other hand, if you have this kind of a tree which I showed you, you require a left rotation. This is done. But suppose the tree is initially 10, 30, 20 like this. Here you would require a right rotation first. That is, you have to bring 20 in the place of 30 and 30 is to be moved on to the right. You get it like this. And then perform a left rotation. So you will be performing left rotation or right rotation. Okay, otherwise in some cases left right rotation. This left rotation is called as LL, right rotation is called as RR, and here in this example what we saw is left right rotation, and here it is right left rotation. So these rotations have to be done to get the trees balanced. Now there is a nice animation of this in some website I will show you, which you can also go through. If you go to W3 school, now consider this binary tree. P is on the left of Q, and as you can see the height of root is -1 and that of the child is 0. So it is quite balanced. Now suppose if I insert D, where do you think D will go? D will go on the left of P. All of you agree? Correct? Now you see that the height is imbalanced. If you find the height of every node, this is 0, there is no left child, no right child, whereas this has one left child and no right child, so it is -1. Here there are two left children and no right children, so it is -2. Now here you have to rotate it right. When you rotate it right, see how the balancing happens. Now if you find the height of each node, you will get all zeros. Is this clear? Rotation of right. Hello?
Yes, sir.
Okay.
Yes.
Yeah. Now if you insert one more, this left will come here. Now simple right rotation or simple left rotation will not help here. You have to perform some left right rotation. Before that, let me add one more C here. If I add C, now still the tree is balanced, because if you find the height of each node, you will see that they are 0 and -1. Now if I add b, now the tree becomes imbalanced. Okay, so this requires a right rotation. So in this case, how the right rotation will happen? So D will come to the center, P will come down, and this L gets attached to P. See how that rotation happens. So rotating the tree involves lot of effort, and only after rotation the tree gets balanced. Okay. Now the purpose of balancing the tree, remember, is that the search operation should take log n time. If the tree remains unbalanced, then it will be much higher than log n. Normally it tends to become n, which is unacceptable in many application situations. So you have to see that after a node is added, you must try to do the appropriate rotation so that the tree remains balanced. Okay, so that was left rotation. Suppose if you had a tree like this, the right rotation, how would it pan out? So it is skewed onto the right now. If I do a left rotation, B will come to the center, and now it is balanced. But now if I add E, it will go on to the right. Here again it is a balanced tree. As you can see, the heights of each node is between 0 and +1, -1 and +1. This is also balanced. But after adding F, which will go on to the right of E, now the tree is imbalanced and you will have a height adjustment required. So here rotate left, you have to bring D as the center, B should become left child, and E should become left child of that, and C should get attached to B. So if I do that, this is how it looks like. Now the tree is more balanced and the search time will be log n. Now AVL trees are difficult to construct, and these rotations involve lot of steps. And if you see the source code of these AVL trees, which I have got it here, it runs into several hundreds of lines of code, almost about 200 lines of code. Okay, now how does it look like? You just have to create a root node and go on inserting the elements. Now if I insert 10, 20, 30, 40, 50 like this, all these will go on to the right. Okay, except that this 25 will go on to the right, onto the left of onto the right of 20, and then onto the left of 30. Okay, so here the tree will be highly skewed onto the right, and you need to adjust that. Height adjustment will be done after the insertion is done. In fact, it will not be shown up in the implementation part. When you are using it, you just go on inserting, automatically the height adjustment will be happening. So there are functions to rebalance the trees. As you can see, you are getting the balance of the tree done if the height is more than 1 or less than -1. Okay, so height adjustment has to be done. So there is a lot of code that has to be written, which we shall not go into, but we shall see the demonstration of this, how this tree works. The output would look like just a normal binary search tree, just that it is adjusting the height. So in order traversal, if I do of this AVL tree, you will see that all the nodes will be in ordered shape, 10, 20, 25, 30, 40, 45. And even when you delete something, height adjustment may be required. In that case also, again the in order traversal will give you the correct sequence, 10, 20, 25, 30, 50. So that 40 will be missing. Okay. Now AVL trees are difficult to implement because frequent rotations have to be done every time you add the nodes. Now what is the solution for this if the rotations are expensive to perform? The solution for this is red-black trees. Now red-black trees are more practical to be implemented with very few rotations required, and in C++, the map data structure we have seen, Some time back I mentioned about map. Okay, there is one more data structure called a set. Both of them implement red black trees, or they are implemented using red black tree concept. Now, what these red black trees are? Red black trees are nothing but the normal binary trees where along with the data each node will have either of the two colors, red color or black color. As you can see, a red black tree will contain each node is either a red or black. That is the first thing. Second is the root is always black. If you see any red black tree, the root will be always marked with black color. And it is assumed that all leaf nodes or the null nodes are considered black. So all leaf nodes have to be black, and if the leaf nodes contain null, they are also considered as black. Then fourth important constraint, red nodes cannot have red children. You will not have two red nodes one below the other. That is the restriction. Okay. And then the last condition, every path from node to its descendant nil nodes contains same number of black nodes. So if you count how many black nodes are there from root till the leaf node, you will see that all paths from the root will contain exactly same number of black nodes. Now consider this red black tree here. The root is black as required. Okay, then all leaf node will be black. That is the left node is null, so that is considered black. Here this is red, its leaf node will be black here and black here. Okay, similarly the red node here will have left. You don't see any red coming one below the other. There is red here, but 7 is black again and again red. You cannot have 7 also red, nor 11 can be red. Okay, so red cannot come below another red. Now if you maintain this coloring, then very few rotations are required. You don't have to rotate many times over. While inserting only, this is taken care of. Okay, so that's the advantage of red black trees. Now the other condition that the number of black nodes should be same. Now if you count the number of black nodes, for example from 12, 5, 3, there are 3 black nodes and the left node is null, that is also considered black. So how many black nodes here? 4. Isn't it? Similarly, if I go this way, 12, 5, 3, then 4, then left, you will see that these 3 will be added and one black that is left. Similarly, if you go on to the right, again there will be one black. So 4 black nodes will be there. So everywhere you go, you will find 4 black nodes. 1, 2, 3, and then there will be 4. Similarly, if I go 1, 2, 3, 4, 1, 2, 3, third black node, and there will be 4th black node at the left side or the right side here. So every path if you traverse, exactly same number of black nodes will be there. So these 4 conditions, if they satisfy, then there will be a red black tree, and this will involve very few rotations of the binary tree to maintain the height balance of the given binary tree. That is why red black trees are extensively used, and the standard template library in C++ implements this particular binary tree. Okay, so let's see the implementation of this in red black tree in C++. So you all have experimented with map data structure. In C++ we saw this. So how do I create a map data structure? I say map will have 2 parts, the key part and the value part. The key is an integer, value is some string or can be an object of another class. So let's say I want to store bank accounts, then I would say map int comma string bank accounts. So in the bank accounts, the key will be 1000 and the customer name is some string like a J or whatever. Then likewise I can go on adding the nodes to the binary tree. Actually what is happening is red black tree is getting created here. Okay, so 1000 will come as the center with the black node, Okay, I'll show you the construction of this. But and adding nodes to red black tree can be done this way or use the insert method. But while inserting, the key value should be specified in flower brackets. That you must take care. And if you want to display the contents of the red black tree, just set up a for each loop where x is a variable of type bank accounts, and you just say x dot first, that is the first part of the node will be your key and the second part will be the value. You have to use the dot operator here. Now if I run the program, you will see 1000 Ajay, 1001 Rajesh, 1002 Nilesh and 1003 Chetana. So you will all be listed in sorted order because this traversal will be in order traversal. Similarly, if you want to search for a given key, all that you have to do is use find method, find 1002 if it is there. In fact, there is no 1002, it is 10,002. Actually, I am just giving a non-existing value. So if it exists, then you are displaying that, otherwise account not found. Okay, so you will run and see that it should show account not found. Similarly, I should be able to erase one particular entry in the binary tree by using erase method. So bank account dot erase 10,002 will remove that account, and if you display again, that account will be gone. So now if I run the program, okay, so this is the original data in the red black tree, and you are searching for 1002 which is not there, so it says account not found, and you have deleted 10,002, and after that if you display, you will see that only 3 of them will come up. Okay, so this particular code here is implementing red black tree. You don't see the colors red black in any part of the code. You just have to go on inserting. Automatically in the background the tree will be constructed, and it will be labeled as red node or black node depending on the requirement. Okay, so if you trace that red black tree, when you inserted 10,000, the 10,000 node came here, the account number 10,000 got created here. So this was labeled as black initially. So root node should be black, this will be null, this will be null. Then we inserted 10,001. So where will this go? This will go on to the right hand side. What color it should be? Should it be red or black?
Red.
Yeah, it can be it can be red or black. Can it be black also? No. Now one other point I forgot to mention, that whenever you insert a node after this leaf node, it should be always a red node. Okay, root is always black, but if you insert next node, it should be initially red node, and if required, this has to be recolored. Okay, next if
I mean, like either left side or right side, it will be red color.
yeah, suppose if you have a account number 9,000 like this, less than 10,000, then this will also be on the left hand side, and it will be red here,
Okay.
isn't it?
After the next means inserting the value. I mean, it can change also. Like this
Yeah,
red can change
it can change also. It needs to be changed because that four or five properties have to be adhered to.
Okay.
Okay. Now, if you see this binary tree, all the properties of the red black tree are satisfied. The first property is root should be black, so that is satisfied. Second is no two nodes should be red. Okay, red should not be below the red. So that is not the case. After black you have red here, after black you have red here. And number of black nodes from root to leaf node should be same. So there is one black here,
Null is also.
then another black here. This is 2. Here also one black, another black, that is true. One black, another black. The leaf node should be considered as black. Okay.
Okay.
Yeah. Now if I add 10,002, then what happens? This will become 10,002 and it has to be red, right?
Yes. And the above one become black.
Now there is a problem. You cannot have red here.
Yes.
Okay, so this time you have to adjust the colors and also maybe you have to rotate. So what he does is he will do a left rotation like this. That is, this 10,001 will come at the root, it will be black. As you can see, this was red, it will be black, and this 10,002 will be red, and on this side 10,000 will come, this will be black, and here there is already 9,999, this is red. Okay, so as you can see, this is also height balanced and number of black nodes will be same.
So actually rotation was not needed, no? I mean this was also a balanced tree only.
But this red how will you resolve?
Okay.
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 So that resolution will help you insert one more properly. If I insert 10,003 now, what will happen? It will come here. So this time no rotation is required.
And it will be black.
Yeah. Now this is red, right? So you have to make this black and this has to be red, and we add it. That's the only thing that is required.
No, why sir?
Because red cannot, when you add any new node, it will be red. If it were red,
Okay.
red will come, no?
Okay, any new node.
Yeah,
Okay. Yeah.
so you should have kept this black only while after rotating, or even when you add node, here you don't have to rotate anything, just have to change the color of the nodes. So this is more efficient than AVL trees. In AVL trees, a lot of unnecessary rotations happen. By keeping the color with the nodes, the rotation can be reduced. Okay, and that is the more practical way of implementing a binary search tree, and that is why in most programming languages all these binary trees which are available in the form of map or set. Okay, the only difference between set and map is set can have duplicate keys, whereas map can have duplicate keys, whereas set will not have duplicates. Okay, for example, we have set can have only the values like this, it will not be key value pairs. Okay, let us say some numbers. So this will also be implemented as a binary tree, and you have to import this set here, or include set. So if I say numbers dot insert, so this is a direct insert kind of a thing. Numbers dot insert 20. Now this is, remember this, it's creating a binary tree with 10 as the root, 20 as the right child. Okay, now suppose if I add 30, what will happen? It will be a skewed binary tree, it will do a rotation. It will bring 20 at the root, 10 will be left side, 30 will be right side, and the coloring will be accordingly done. That is 20 will be black, 10 will be red, and 30 will be red. Okay. And if you print this value, they will be in sorted order. So only thing is you have to imagine what is happening in the background. It looks like you are inserting some data into an array, but this is not an array, this is a binary tree, okay, which is perfectly balanced almost all the time. And if you want to display, then it can be in text, numbers, cout. I think so we have to okay, set 20, 25, 30. So we get the list in the sorted order. So both of these are uh, red black trees. Did you follow what we have discussed so far? The usage part is very simple, but what you need to understand why map is different from your vector and how do they differ. If I use vector, similar thing you are doing. You are just doing insert, insert, and then displaying. But when you do a search, that would take longer time than a map. Okay. So here I am searching for 1002. If I make it 10,002, since it is present here, it will display that value also. Search an account not found is there. Now since I am giving 10,002 which is there, it will display that account. As you can see, I search for 10,002. After searching, that account is found, it is displayed here. Okay, so this will work much faster. Okay, so you just try implementing this part. We have done this before also, but you have a better understanding now that why maps and why not vectors. Okay, you can compare this with vectors. In vectors also I can store numbers, isn't it? For example, if I have vectors, let us say nums. This can also store numbers, but the difference is vectors is a normal array, whereas set is a red black tree. In this also we can insert values. Exactly the same way I can insert. This will also give the same output displaying, but when you no instance, okay, so there is no insert taking only values. I think so it is push back, and you can use push back instead of insert is calling pushback. That is the only difference. But the difference comes when you want to perform search operation. Okay, so when you search in a set or a map, this will take log n time, and if you search in a vector, it would take order of n time. But if this is not an issue if you have only 4 or 5 elements stored, but imagine there are 100 elements stored, then on an average you might perform 50 operations when you do the search, whereas if it is a set or a map, you will be performing only 6 or 7 operations to reach out that particular element which you are searching. Okay, so is the idea of balanced binary tree clear? Hello?
Yes, sir.
Okay.
Got it, but still bit confusion is there.
Okay. Okay. Now just do this implementation, right? Using map and try it yourself.
Okay. Okay.
We have done all this before, but only with no knowledge of what map really is. But now you got some clarity that map is a binary tree and is a red black tree. Okay.
Sir, even set is also a red black tree.
Yeah, set is
Only
also red
vector
black.
is a normal array.
Yeah, vector is a normal array. So just try one thing. Numbers dot insert 10 again. Let us see whether it throws some error. Okay, so it doesn't show up that 10 again. Even if you insert a duplicate, it will not show it 2 times, it will show only once. Whereas if you in the map, if I do bank accounts 1000 again, 10,000 again, let us see what happens now. Whether that 10,000 will be shown twice or it will be shown only once. It will be shown twice. Map allows duplicates. Oh, what happened? Okay, this will overwrite that 10,000. Okay, so that this is again not allowed. I'll just come back with that clarity next time, whether duplicates are allowed in maps or not. So for now, in set, if you try to put a duplicate, it will not be displayed again. See, in more practical case, you will have a account class, and this map which we have declared here can be int comma account.
Hello.
Like this. So this is another practical possibility that Second part is not just string, it is an object of account class. In fact, we have done this when we are discussing maps in C++. This will be an object of account. Of course, you should have defined constructor there. So you must have a constructor here. Object of another class. So in a large application where you have hundreds of accounts, using a map would be helpful to insert the account objects as many as you want, and that remains balanced using the red black terminology. And every time a new node is inserted, it is labeled as red, and if there is a rebalancing required, the rebalancing will be done automatically. And when you perform a search, the search would happen pretty fast. So just implement this and see for yourself how the insertion has to be done, how the search has to be done, and then how the display has to be done. So insert some data into the data structures and perform display and search operations like this. Arpita, some time back you had asked how to decide whether to use vector or map. Okay, so here you have to observe which operations are you are doing frequently. If you are doing too frequent insert operations and performing search operation, then a map is better. Okay, but if you are only accessing one of the element randomly, then you can use the indexing and get the element searched in fixed amount of time.
So in that case, map uses what you're telling, sir.
Pardon?
If you search with particular, then map is not the suggested.
No, randomly if you are searching any element from the collection, then vector is better.
Okay, with particular index we are going to search.
Index only you will get it. But suppose you are doing insertions in between, because in array you can only, in vector you can only push to the back or put at the beginning. You cannot do insertion in between. If you try to insert in between, it will take pretty long time. You have to shift the elements and make room for it. Okay, so that is going to take a order of n time if you do insert in vectors. Okay, but frequently more customers will be added to the bank and you have to insert them according to their names alphabetically. So insertions will be happening, so their map is much better or preferred data structure to be used.
Okay, okay.
Yeah.
Thanks, sir.
Okay, so to summarize, we looked at balanced binary tree in the form of AVL. AVL is less practical to implement, and it runs into several hundred lines of code, and that's why it is not implemented in C++. An alternative to that is either a set or a map. Set allows you to store only one value, and duplicates are not allowed, and map allows you to store key value pairs, and here duplicates are allowed. Okay, so I'll come back with the clarification whether duplicate is allowed, and if yes, how it will show up in the output next time, and we'll discuss another important data structure, that is heap. Okay, and then we shall try to conclude in the next session. All right, shall you close for today?
Sir, just the code part I wanted to see in the end.
Okay, just
It's the last 4 lines.
yeah. I'm just deleting one node from the binary tree using erase method.
And then print.
Yeah, and print it.
Okay, sir. And that AVL tree code you will be sharing it, right, sir?
I'll share, but you will only notice that there is a lot of
Okay.
effort required to do the balancing.
Okay.
Okay. I'll share the code.
Okay, sir.
Okay then. Yeah.